Greetings everyone, we're going to be talking about work and energy. Here we have myself and Dr. Andreessen pushing on the car. That push is going to be this force moving to the left, and we're also moving the car to the left, so this gives us our displacement. Work is the product of these two vectors. This kind of product is called a dot product. And it's a special way of multiplying two vectors with each other. The result of this is just a scalar, so work is just a number. There's no direction associated with the work, but the relationship between the force and the displacement, the angle between these two vectors will come into play, and we'll see that. So here we have work as the dot product of force and displacement, as I said, and where that angle comes into play is right here. So how we do a dot product is we take the product of the two magnitudes of the force and then displacement, and then we multiply by the cosine theta. So if here is an object M and it's moving some displacement x, we're applying some force F, then the angle is this angle between the two of them. And so you can see pretty clearly here, if theta is 0, then cosine theta is going to give you 1. If theta is 90 degrees, then cosine theta is 0. So if the angle between these two, the force and the displacement, is 0, then the work is just going to be the magnitude of F times x. If the force is perpendicular to x, like maybe the gravitational force might be on this object, then it's not going to be doing any work on the object because the force and the displacement are at right angles to each other. So then the dot product of those two would be 0. But this force, the dot product of this force times this displacement will give you something, because cosine of this theta, maybe this is 30 degrees. Then we just need to multiply the magnitude of force times the magnitude of x. Is going to give you this 30 degrees. We'll go over a bit more of these things and talk about this relationship, this dot product and the cosine theta in a little bit. But now let's consider how can we conceptualize work? What exactly is work? Well, if we look at work, let's just take this, and for the simplest case, let's say F is in the same direction as x. So Fx. In this case, maybe it's an object that's falling down through the force of gravity, so x is going to be this way too. And in this case, force of gravity and x are in the same direction, both pointing down. We know what the force of gravity should be. And we can go back to this to put some numbers to what we're getting here. So work is force times displacement. And so force is just ma, and then now we're doing our displacement x. If we go back to our kinematic equations, we have v final squared is v initial squared plus 2ax. Right here is our ax that we're going to want to put into here, so I'm just going to solve for this ax. Ax is going to be 1/2 v final squared minus v initial squared. So if I plug that into here, I'm going to get work is equal to m, and then this 1/2 v final squared minus v initial squared. And I can rewrite this to be 1/2 mv final squared minus 1/2 m v initial squared. And this is starting to look familiar. So this is our final kinetic energy minus our initial kinetic energy. So this is really just saying work is going to be the change in our kinetic energy. So if we look at, go back to this falling object. So however much work gravity does on this object. So let's say that the object, maybe here we have a ball m, and at this time velocity is 0, and then we drop it and it falls down 1 meter. So what is the work that gravity does on this object? So that's just going to be force of gravity, that's just mg, times x, which is 1 meter. and this is going to be equal to our change in kinetic energy, which is just V final minus V initial. In this case, V initial is 0, so this is really just our kinetic energy is going to be mgh. So this is a very similar thing that we saw with our potential energy, but here we're using work in order to derive how this kinetic energy is related to the potential energy. Here we have Lao Hui at the Beijing Olympics, and he's holding, I think this mass is 158 kilograms. It's quite a bit. And he's holding it above his head. And so this sorry, let's change color here. And so the force of gravity on this object is this 158 kilograms times 9.8. That's the force of gravity pulling down on this weight. And I'm telling you that Lao Hui is not doing any work here. Even though he's straining, you can see his neck, his arms, he's straining quite a bit. So why isn't he doing any work? If we look at the definition of work, work is this F dot X. So here, the dot product does matter. So the work that he is doing, he's pushing up. So this is the force that Lao Hui is doing. But the displacement on this object is 0. So here, if this X is 0, then the work that he's doing is 0. So since the object isn't moving, he's not doing any work, but he's certainly straining quite a bit. Let's consider a different case of not doing any work. Here we have a car, gravity is pulling down, but in this case, the car definitely does have some displacement. It's traveling at a constant velocity. But gravity is pushing down on it. We have a normal force pushing up. We can even have a frictional force pushing back in this direction, and then the force of the engine in this direction. But in this case, since it's traveling at a constant velocity, then these forces, FF, we look at the sum of our forces, minus FF plus FE of the engine is going to be 0, because this is mass times acceleration. If V is constant, acceleration is 0. So these two forces balance out, so there's no net force in this X direction. There is also no net force in this Y direction. In the Y direction we have Fn minus Fg, and that's also going to be 0. So this F net in our Y direction is also 0. So there's no net work done on this car. And another way that we could see that this is done is that work is the change in kinetic energy. And since this car isn't changing its velocity, its kinetic energy can't change. So we can have both positive and negative work. And where this really comes into play is the direction between the force and the displacement. So until now we've just been considering positive work where the force is in the same direction as the displacement. So if we look at work, this is F dot X, which is equal to Fx cosine theta. So in this case, theta is 0, theta is also 0. But if you want negative work, what you need is the angle between these two to be greater than 90 degrees, right? Because then cosine of something greater than 90, over here somewhere, is going to give you a negative number. So here we have theta is 180. So in this case, this force would be doing negative work on this object. So it is actually slowing the car down. So you can look at the work is the change in kinetic energy. So if you have negative work, you are making K final minus K initial. If it's negative work, then that means that K initial is bigger than K final. So it's slowing down. In the case of positive work, this side over here has to be positive, so K final has to be bigger than K initial. So you're speeding the object up. Let's consider this video again. So obviously, me and Dr. Andreessen are doing some work on this car. It now has some kinetic energy. Initially, it was at rest, so we did some work. Let's find out how much work we did. So the mass of the car is 1,500 kilograms. We pushed it 18 meters, and we did this in 13 seconds. So how much work was done? And this is what we want to find out. So what we need to know is work is equal to force times displacement. So we need to draw our free body diagram. So here is the force that we were applying on the car, and then we pushed it from here all the way over to here. So this is our X. We can see that the force and the displacement are in the same direction, so I really just have F magnitude X. Cosine theta here is just going to give me 1. So the distance that we pushed the car was 13 meters. And we can figure out what the acceleration of the car was using kinematics. And so then we're going to get A is going to be 2x over t squared. And this is going to give me 0.21 meters per second squared. So then the force on the car is going to be mass times acceleration. So that's 1,500 kilograms times this 0.21 meters per second squared. And this is going to give me 320 newtons. So then the work that's being done is going to be Fx, which is going to be this force times the displacement. So this is going to be 18 meters times this 320 newtons is going to be 5,760 joules. So the units of work are in joules, which matches what the units of kinetic energy. So another important thing about work is that we could break up what's being done here. So until now we just considered work to be F times X, but what if work was what if the force was a function of X, right? Then how do we do this? So basically what we have to do is to do an integral here. So let's take a spring. So force of the spring is going to be Kx. So this is the force applied to the spring, right? We want to know how much work does it take to compress the spring. So work to compress spring is what we're going to find out. So before we talked about this minus Kx, but since this and the force applied by the spring are interaction pairs, then this one will be positive. So, right, the force we said was minus Kx. Since these two forces are equal and opposite, this guy's got to be positive. So this is the force to compress the spring. All right, so this force obviously depends on X, how far we are compressing this spring. So here's our mass. We want to compress the spring. Here's this equilibrium position. And then now we're going to compress it some dx. So then the work is going to be the integral of this kx dx between these 2 points, x1 or x0, or wherever we start and wherever we end. When we do this integral, we're going to get 1/2 k x2 squared minus x1 squared. So if you want to know how much work is being done, we could also look at the force versus x, the area under this. And here I have a quick plot showing you, here's the spring force versus x, and then here's the associated energy. So at 2, if we compress this spring 2 meters, then we're going to get 20 joules of, it's going to take 20 joules of work in order to compress the spring 2 meters. So you could do 1/2 B times H, right? So 1/2 times 2 is 1 times 20 is going to give you 20 again. Alright, so now let's work a few problems. Here we have some mass sitting up here. It's 2 kilograms, and it's going to slide down this ramp. Then all along here, we're just going to say that friction is 0. So we're not going to worry about any work that friction is going to do here. And then the mass is going to have some velocity down here. And it's going to keep traveling until it runs into the spring. When it runs into the spring, it's going to start to compress the spring, which is going to require some work. So at the top of here, we have all U gravitational energy. Our kinetic energy is 0, this thing's at rest. But then when it slides down here, all that UG is going to be 0, because I'm going to say that this line right here is going to be UG equals 0 line. So here, UG is 0, but my kinetic energy is going to be big. And then it's going to keep sliding, so nothing's changing. And now, it's going to take this kinetic energy and convert it into spring energy that's stored in the spring. So let's find out how far the spring compresses. So what we know is that energy initially equals energy final. So this is our energy conservation. So the energy that we have initially is mgh. And the energy that we have final is going to be all spring energy, so 1/2 kx squared. So then now we need to find this h. So this h is going to be how high this is. This is our h. And here we just have the hypotenuse. So I know that the sine theta is equal to h over 1, where 1 is my hypotenuse. So then h is just going to be sine theta in this case. Sine theta times that 1 meter. So now I have mg sine theta basically times 1. It's going to be 1/2 kx squared. And then I just solve for x. So x is going to be the square root of 2 mg times that sine theta all over that k. So this is going to give me about 7 centimeters when I work this out. So another way is to think about what is the work done on this box. And so here we have the box right here, and the force of gravity is down, but the displacement is in this direction. So then I really need to think about this theta here. This theta, let's change colors real quick. This theta is 60 degrees. So when I do mg times the distance that's done, so that's the 1 meter, and then now I need to do cosine 60. So this cosine 60 is the same as this sine 30. So this is sine 30 degrees. Sine 30 is the same as cosine 60. And so I would end up getting the same thing here. Is if I look at my energy initial is equal to energy final. When I plug this in, I'm going to get my energy initial. I have no kinetic energy. That guy is 0 initially. Plus the work that I'm going to do, the work that's done on the object, is going to be my final kinetic energy or my spring energy. It just depends on what I'm looking at. So then the work that's done on this box is going to be completely converted into the spring energy. So this is this mg cosine 60. Here we have a high-speed train, and we're going to be using its emergency brakes to slow it down from 54 meters per second to rest, and it's going to take 850 meters. Alright, so let's draw this out. So here we have our big train. It's moving with some initial speed. Then the emergency brakes. So what do the brakes do? So the brakes are slowing this guy down. So that means that the force has to be back, pushing against this speed. And then the final case is going to be it's at rest. So the displacement that this thing takes is this 850 meters. So then work is equal to K final minus K initial. So K final is 0, so this is really just minus K initial. And then this work is equal to force of the brakes times the distance that it took. This is a big K. And so what I'm going to do is going to say that the force applied by the brakes is going to be constant. So I'm going to solve for this FB. It's going to be minus K initial all over X. So now I want to know how far the train will need to stop if it's traveling 85 meters per second. So in both these cases, I'm assuming that the force of the brakes is going to be the same. So it's just going to take longer to stop the train when it's going faster. So then basically I have FB1 is equal to FB2. So this tells me that I'm going to have my kinetic energy 1 over x1 is equal to my kinetic energy 2 over x2. And then now I'm just really looking for this x2. So I'm going to solve for x2 is equal to x1, kinetic energy 2 over kinetic energy 1. So then this x2 is equal to this 850 times kinetic energy 2, that's 1/2 m v2 squared over 1/2 m v1 squared. And I find that x2 is going to be 850 times 85 squared over 54 squared. And this is going to be 2,100 meters or 2.1 kilometers. Alright, so here we have a 2-gram grasshopper launching itself from rest, and it accelerates its center of mass through 1.5 centimeters. So what this means is that from here where it leaves the ground to where it starts, it needs 1.5 centimeters. And then if the average force is delivered is this 2 newtons, what's the max height it could jump? So grasshoppers don't jump straight up, but we want to know if it was just jumping straight up, how high could it jump? So let's use work energy in order to work this out. So this is going to be a change in kinetic energy. So this is K final minus K initial. Another way that we can think about this is energy is equal to energy final. So initially, the grasshopper is at rest. Then the grasshopper is going to do work. All that work will be converted into kinetic energy, right when he's leaving the ground. Then he's going to travel up use up all that kinetic energy and get to some height. So that height is going to be this mgh that we're going to look for. So really the work that's being done is all going to go into this mgh. So the work that's done is F times x. So what is that force? Force is 2 newtons. So then 2 times 15 millimeters is going to be equal to mgh. So this is 2 grams over 1,000. And then 9.81, and then all the h that we're looking for. When we solve for h, we're going to get 1.5 meters. So if the grasshopper wasn't just jumping at some angle and he decided to jump straight up, he could go up 1.5 meters. So in our final problem, we're going to be looking at a bungee jumper. So you are the bungee jumper in this case. So you're going to jump off this bridge, and then you want to set, so the bridge is 200 meters above the water, and the spring constant of this bungee jump, so in this case, here's your bridge. First you start off right here, and your velocity is 0. So this is the total height, right? And then here's the water down here. So then you're going to fall down some distance. Let's just call that distance A. Let's just call this distance A. Then the rope is going to start to stretch. So at this point you can see that the rope isn't really taut, it's not pulling against you, but after you fall this distance A, now it's going to start pulling. So after it starts to pull on you, you're going to stretch the rope, and you want to just end up with V equals 0 right above the water surface. So this would be a very hard problem to work with if you just had to use these kinematic equations, because you have to start up here, look at how far you fell, now you have some velocity. We don't know what that velocity is, and then now you're stretching, so this force is actually dependent on the height, right? Because that's the minus kx, right? And then now it's going to end up stopping you, and you want to know how big should A be, basically. So A is how long is the rope. So A is what we're looking for. And this would be very hard to work out with just kinematics, but we're going to use work energy. So here we have E initial equals E final. So let's look at the kinds of energy that we have here. Here we have basically just UG up here, and that's mg h of the bridge. Then what's going to happen is you're going to fall down, convert some of this gravitational potential into kinetic, and then you're going to stretch the spring. So that energy is going to go into stretching. So that's basically down here, all the energy is being converted into spring energy. So 1/2 kx squared, where this is like the distance that this rope is stretched. So initially we just have UG, and finally we just have US. So this is just mgh, and this guy is just 1/2 kx squared, where this x is this distance right here. So then we could pretty easily solve for x. X is going to be square root of 2 mgh over k. And we could work this out. We're going to get 74.12 meters. So then how long does the rope need to be? So the total distance is this 200. So what you want is 200 is going to be equal to A plus the 74.12. So then A is going to be 125.88 meters.